Okay, so hi everybody. So it's lecture 25. And this is going to be, so let me just say what we're going to do in this lecture. So we're going to finish talking about second order homogeneous ordinary differential equations. In particular, we're going to talk about the case of complex roots, which we didn't get to cover last time. Then we're going to talk about the initial value problem. Which is some, so far we've been talking about how to find a general solution to this kind of equation. Then today we're going to talk about this initial value problem, which has a lot of physical significance. And then we're going to talk about systems of first order ODE. So, so this is, the content of chapter 9 in Lay. So let's see. So one important, because of the way the last few lectures went, the material from the second order ODE part was kind of scattered across 3 lectures, which is maybe a little bit confusing. So what I've done is I've on the course website, I've written some notes here. If you click on Nikhil's notes next to any of these lectures, I just sort of written sort of self-contained notes about the second order ODE stuff. Since the book is kind of disorganized and the lectures were also kind of scattered, you can refer to this if you're feeling lost. So you can follow that. And also, one important remark is that since we're a little short on time, and because I think the contents of those sections are kind of the most boring thing in the whole course, we're going to skip sections 4.4 and 4.5, which is something called the method of undetermined coefficients. You can do it, it's optional. In my opinion, it's not very interesting, but you can do it if you want. This is not going to hinder you if you're actually a physicist and want to solve differential equations, because if you're actually doing this in any real context, you're going to do some much more sophisticated version of these sections from scratch anyway. So I don't think there's anything lost. Okay, so so let me begin with just remembering what we did last time. Or last 2 times even. So last time we talked about these homogeneous second order ordinary differential equations. So we talked about equations like this. And we're looking for solutions y of t, which are, some infinitely differentiable function on R. That's an unknown function. And we sort of realized that this is equivalent to solving, to finding a vector y in the kernel of a certain linear transformation, t, where t is a linear transformation from infinitely differentiable functions on R to infinitely differentiable functions on R. And what it does is it does this differentiation that's shown on the left-hand side, right? So t of y equals ay double prime plus by prime plus cy. And we also had sort of this fancy notation that we used last time that was useful, which is you can write t as a sum of multiples of the second derivative operator, the first derivative operator, and the identity operator. So there's a different notation for the same thing. So last time, we studied the setup and we had 2 questions. The first question is find the general solution. That means find all y of t that satisfy this equation. That just means find the kernel of this transformation. And the second type of problem was find a particular solution in the kernel satisfying some initial conditions, namely y of 0 and y prime of 0 are equal to some specified values. So this is called the initial value problem. And these were related by this important theorem, which is now from 2 lectures ago, which was that the linear transformation, sorry, not TS. So we defined another linear transformation from the set of solutions to this homogeneous equation. So this is the key equation here. Just to R2 just by evaluation, which I think we've seen in the course several times by now, even in homework and exams. This is an isomorphism. And so in particular, that implies that the initial value problem always has a unique solution. For every initial data y0, y1 in R2. So that's a recap of things that have been discussed over the last 2 lectures. And in the last lecture, we made a lot of progress on the first item, which is how to find the general solution. So let me just recap that now. So in the last lecture, we have this auxiliary equation, right? So ay double prime plus by prime plus cy equals 0 for an exponential function if and only if ar squared plus br plus c equals 0. So that's an algebraic equation. This is the auxiliary equation, which by now I guess you've done some homework about. And this allowed us to, in many cases, find the general solution, right? So we had these 3 cases. We covered 2 of them last time. So the first one is, the cases are on the discriminant of this quadratic equation. The first one is that the quadratic equation has a positive discriminant. And in this case, you have 2 distinct real roots. And the second case, okay, now let me write down what the general solution was. In this case, the solution was just the span of the exponentials given by these roots. The second case is when the discriminant is 0. And in this case, you just have 1 root. You don't have 2 real roots. And this required some ingenuity to figure out, to somehow extract another solution from this case. But we did it last time. And in this case, the solution is given by an exponential function and some function which is not quite an exponential. It's t times e to the r1t. And I might have done this a little quickly last time. So I wrote about it in detail in the notes that I mentioned earlier. So you can read about this in detail. And what we're going to do today is the last case, which is you have a negative discriminant. And in this case, as you know, you have so this has some roots, right? So, and these are given by the quadratic formula, right? So in this third case, these roots are, going to be complex, right? So you have two roots, R1 equals some alpha plus I beta, R2 equals alpha minus I beta, where beta in this case is going to be whatever you get from taking the square root of this discriminant, right? So here, let me just remind you, beta, oops. Yeah, so here beta is square root of 4ac minus b squared, right? Because you're taking the square root of a negative number, you're going to get I times whatever the square root of the positive, the absolute value of it is, which is this. So in this case, you have two complex roots. And in this case, we're now going to discuss what are the solutions of the differential equation. So any questions about this recap? Okay, so C for complex. Okay, so let's discuss the case of complex roots. So you have this AR squared plus BR squared plus BR plus C equals 0. Has roots. R1 equal alpha plus I beta. R2 equal alpha minus I beta. So, you know, this is kind of a drag, right? Because you can't, if you just look at e to the, so you know, what's the issue? The issue, well, okay, before I even get to the issue, let me do a review of complex exponentials. Okay, so in the previous case, the way the roots were related to the solutions of the differential equation were by taking exponentials, right? With that root in the exponent. So in the case of complex roots, we're going to have to use complex exponentials. So let me briefly do that. So this is a brief review, or if you haven't seen it, intro to complex exponentials. Okay, so what is a complex exponential? Let me define it. So if you take e to a complex number, then that is, or you know, let's, since we'll be looking at numbers like this, let's just do it like this. Or actually, we don't need to write t. Let's do it like this. So e to a complex number. How is it defined? It's just the power series. So it's 1 plus that number plus the number squared over 2 factorial dot dot dot. Same as before. That's the definition. That's the definition of a complex exponential. It's an infinite series, which we won't prove it in this course. It always converges to something. Now, that's a well-defined series. Now, what are the key properties of this complex exponential? So there are 3 key properties. I mean, there are hundreds of key properties, but for this course, there are 3 key properties. The first property is that differentiation works the same way. If you take the derivative of e to the alpha plus I beta times t, which is now a function, right? So I can put a t in there and it's still, you know, it's a well-defined function of t, right? Then this is still the same. So differentiation works the same way. And, you know, maybe this is the kind of this is a complex valued function of t, which is, right? Which is still assumed to be real. Okay, so you can define derivative for this. And I mean, it's the same thing. The differential is the same, and it works the same way. Exponentials still have this nice property that when you differentiate them, you know, something very nice happens. So any questions about that key property?
Is this property, like, can we just see it? Or how do we know that it's true?
Well, so I'll actually show you a proof based on maybe the third key property,
Okay.
if you haven't seen it before. But yeah, so maybe I should have done a different order. But let me show you the other key properties. So the second key property is if you if you take an exponential of a complex number, it's just equal to e to the alpha times e to the I beta. So this is like exponentiation for real numbers. It works the same way. This you can verify from the series. We won't do it now because it's a little bit boring, but it works the same way. So this is a familiar property. But the third property, which we will verify, which is very beautiful, is that if you take e to the alpha plus I beta, that's equal to e to the alpha times, or let me write it like this, e to the alpha cosine beta plus I e to the alpha sine beta. So this is called Demofra's identity. I don't know where the apostrophe. Okay, whatever. And this we will prove right here. It's a very beautiful proof. Well, so e to the alpha plus IB is equal to e to the alpha times e to the I beta by property 2, which we didn't prove, but let's just believe that for now. And now let's expand this in a power series. This is e to the alpha times 1 plus I beta plus I beta squared over 2 factorial plus I beta cubed over 3 factorial dot, 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 dot. That's the definition. So now let's think about what these terms actually look like. So let's do a little side calculation here. So what is I squared? Well, that's minus 1, right? What is I cubed?
Negative I.
Negative I. What is I to the 4?
1.
1, okay. So you kind of see this this pattern that as you take powers of I, alternating terms are real and complex, right? So the even terms are real with alternating signs, and the odd terms are complex with alternating signs. They're multiples of I. So what I can do is I can now arrange these terms separately. I can write this as e to the alpha. I can collect all the even terms. So I get 1 minus beta squared over 2 factorial plus beta to the 4 over 4 factorial dot, 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 dot. And then I can collect the terms that have an I in them, right? So I have e to the alpha and I take the I out front. And what do I get? Well, I get beta minus beta cubed over 3 factorial plus beta to the 5 over 5 factorial dot, 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 dot. Okay, so does anybody recognize those series?
Cosine and sine.
Yeah, that's just the Taylor series for cosine and sine, right? So this follows from the definition. This is e to the alpha cosine beta plus I e to the alpha sine beta, right? So the proof is not hard. It's just Taylor series. So these are the 3 properties we're going to use of complex exponentials. And I mean, this last identity, it's people sometimes, this is one consequence of this is that e to the I pi equals minus 1 and things like that, right? Which are really some very beautiful identities. But the proof is actually easy. It's just Taylor series. So any questions about this review? We're going to use this in a moment. Okay, so let's now go back to our differential equation, right? So back to this equation. So we have this equation, ay double prime plus by prime plus cy equals 0. We have this auxiliary equation, ar squared plus br plus c equals 0, has roots r1, r2, which are these alpha plus I beta, alpha minus I beta. Okay, so the idea is, well, you know, the reasoning on the first slide, sorry, the reasoning on this slide. So this, let me call this is the sort of key reasoning, right? Okay, that shouldn't have gone through there. By this reasoning, this actually still works for complex exponentials, right? Because differentiation works in exactly the same way. So the same argument actually works. If you plug in a complex exponential here, you can cancel the e to the rt and get an algebraic equation, right? So by property 1, essentially, star still works. So the key idea is, so idea, consider a complex solution, e to the alpha plus I beta times t, or maybe both of them, e to the alpha minus I beta times t. Okay. Now by property 1, differentiation, the only property used that differentiation works the same way, these will still satisfy the equation. So these satisfy the equation, the differential equation, by this thing that's in the box called star. So by blue star. Okay, but we're not happy, right? Because so, you know, one way of writing that is, if you take this linear transformation t and apply it to e to the alpha plus I beta t, this is 0. And if you apply it to e to the alpha minus I beta t, that's also 0. Okay, why are we not done? Looks like we found 2 solutions.
They're complex solutions, not.
Yeah, they're complex, exactly, right? So the issue is that these functions, these are not in our vector space of real valued functions on R. So there's like a really sort of slick trick to fix this. Okay. There's a way to extract some real solutions from these complex solutions. And this trick kind of is very useful. So here's a trick. Well, you know, we have these 2 solutions here, right? And I know t, so here, okay, I'm doing something a little bit shady. I'm temporarily considering t to be on complex functions. That's okay. It's the same definition. Now that's still a linear transformation, right? So the trick is, t is a linear transformation, right? So I can add these 2, I can add the 2 equations in the red box. So I have t of e to the alpha plus I beta t plus t to the e to the alpha minus I beta t equals 0, right? But now I can use linearity. And this is just saying t of the sum is equal to 0. And again, by linearity, if I throw in a factor 2 here, it's not going to change anything, right? by linearity. Okay. And now there's something nice that's going to happen. I'm going to use this Demofra's identity. These, right? These exponentials are actually just, I can write them as, I can write the real and imaginary parts in terms of sines and cosines. So what I get here is a t of e to the alpha t cosine beta t plus I e to the alpha t sine beta t plus e to the alpha t cosine beta t minus, sorry, there's a minus I e to the alpha t sine beta t divided by 2 is 0. But now this is the clever part. These imaginary parts just cancel. And now I do get a real solution, right? And this is a real function. Okay. So given a pair of complex solutions, I extracted a real solution. Okay, somebody asked about the half. Let me just throw in the half here just to make it clear. Right? Okay. So any questions about this derivation?
I'm a little bit confused why there's an over 2.
Oh, well, I just put the over 2 because, in the bottom here, otherwise I would get 2 times e to the alpha t cosine beta t. So I just put the 2 to cancel that out. I mean, otherwise I would have got 2 times that and it wouldn't have really have changed anything. But I could have divided by 2 at the end also. Does that answer the question?
Yes, thank you.
Any other?
Would it be correct to consider real numbers to be a subspace of complex numbers, or real functions to be a subspace?
So that is an excellent question. So it's a very good question. So are real functions from R to R? So let's define 2. So let me just write down the set. Is the set, let's say F, the set of a subspace of, let's say, this vector space. This is all complex functions, right? Okay, so the answer depends on what you mean by subspace, right? So subspace means it's closed under taking linear combinations, right? But in that, you have to be clear what you mean you have to be clear what you mean by scalar multiplication, right? So the answer one is it is a real subspace. So what that means is, if you take a function in F and multiply by a real number, you stay in F, right? Right? So if you add 2 real functions, you get another real function. If you multiply by real numbers, you get another real function. It's fine, right? But there's a second equally valid answer, which is it is not a complex subspace. Now, we haven't really developed these concepts. So what that means is if you use complex scalars. Why is that?
Because if you multiply with a complex number, it will no longer be in the real to real.
Exactly. Example, you have, let's say the function I don't know, e to the t is in F, but I times e to the t is not in F. Not closed under multiplication by complex scalars. Okay, so this is a subtle point. It's a very good question. We will not be emphasizing this in this course. You'll talk a lot more about these kinds of questions in Math 110. But the point is, the definition of a subspace assumes, you have to be very explicit about what you mean by scalar multiplication and addition, because the answer depends on that, on what the underlying scalars are. Great question. Any questions about this? This is sort of an aside. But going back to this, so now we found a real solution. Anybody see how to find another real solution? Remember, we want two real solutions, right? The kernel of T is a two-dimensional subspace. We need two solutions. How are you, any idea about how to find another one?
Can we subtract the second transformation from the first?
Yeah, exactly. Yeah. So to find another solution, let me do it in a box here. Let's subtract them, right? So you have e to the alpha plus I beta t minus e to the alpha minus I beta t. So this time I won't do the 2. I mean, okay, well, I'll do the 2. Why not? This time I'll divide by 2i. By the same reasoning, you get that this is t of 2i e to the alpha t sine beta t over 2i. And then these cancel. Equals 0. And so you get that e to the alpha t sine beta t is a solution. Okay, so you can check that these are linearly independent. It's actually not hard, so I won't do it in the course. But now we're done, right? So let me write down the summary, and then I'll do an example. If the auxiliary equation has roots R1, R2 equal to alpha plus I beta, alpha minus I beta, the kernel of T is the span of e to the alpha t cosine beta t and sine beta t, which are now legit real functions. And this is, you might find this a little surprising because we started with a real problem, right? There was no mention of complex numbers, but to solve it, we had to use complex numbers. And this is really sort of a beautiful thing that happens a lot in math. So I mean, Poincaré even had a quote about it. This is true all over the place, that he said that the shortest path between 2 points in the real domain passes through the complex domain. And I mean, this happens a lot in math. That you want to solve a problem of real numbers, it's helpful to do complex. And since this was a bit abstract, let me do an example. So what was the equation I had? So the equation was, yeah, y double prime minus 4y prime plus 5y equals 0. So you form the auxiliary equation, r squared minus 4r plus 5 equals 0. So r equals 4 plus or minus square root 16 minus 20 over 2, which is 4 plus or minus, I guess, 2i over 2, which is 2 plus I 2 minus I. So here alpha is 2 and beta is 1 in the notation of the previous slide. And so now what are the solutions? So what's the general solution? Well, or what are the solutions? Well, according to what's written on the previous slide, it's e to the 2t cosine t, because beta is 1, and e to the 2t sine t. And so, the general solution, you can express it as y of t is a linear combination of these two things. And this is just another way of saying that the kernel is spanned by these two vectors. So that's a concrete example. And now we can, complete our summary in the first slide, or in the second slide, that we know now that the solution in this case is span of e to the alpha t cosine beta t, e to the alpha t sine beta t. So that's it. These second order homogeneous differential equations are completely understood. There are three cases given by what the roots of the equation look like, and they're just listed here. And this like complex number stuff, it's not just intellectual curiosity. It's not just some like weird side case, because these things have a physical interpretation, right? So in the physical equation is like whatever my double prime plus cy plus y prime plus ky equals 0, where you have the spring system, right? And if you plot these three cases of what the roots look like correspond to different physical behavior. Like in this case, you have exponential growth or decay. Whereas in the bottom case, you have oscillation, right? Because these sine and cosine, you know what they look like. They oscillate. And they eventually die out. That's why they're exponential terms in front. And this case in the middle is sort of a critical case. So in physics, the first case is called overdamped, the second case is called critically damped, and the last case is called underdamped. And you can, you can play with these in the spring simulator and really feel what these different cases mean. So we had this like spring simulator here. So these are the three coefficients m, c, k. And so you can plot what this looks like. So this is falling in the third case, it seems like. But now if you make b squared minus 4ac positive, which means you have to make the friction, the damping really high. So let's make this 10. Right? So now if you do this, you get a very different behavior. It doesn't oscillate. It just dies. Right? That's the exponential. That's case one. So this is not some like abstract thing. It's something that really appears in mechanically. Right? And on the other hand, if you make the damping 0, no friction, then you see a very different behavior, right? You see a pure sine function. So these sines and cosines and complex exponentials they're like a real thing. They're not, they're not some weird like side case that's going on here. Okay, so that's all I want to say about homogeneous second order ODE general solution. Any questions about that?
What do you mean by critical?
Yeah, so critical means in physics it means if you increase the damping a little bit, it'll just decay exponentially, and if you reduce it a little bit, like any amount, it'll start oscillating. This is a physical term. I'm not defining it mathematically.
Okay, thank you.
Any other question? Okay. So now I want to briefly discuss the initial value problem. for second order homogeneous ODE. And this problem is, this is very straightforward. Oh, did I just clear the slide? I guess I know how to undo now. So this is what's written here in the first slide. I figured out how to find the general solution, which is just find all functions that satisfy the equation. But now, if I really want to simulate a spring, then what I want to know is, given the initial position and velocity, what happens, right? And that adds one more piece of information to the problem, which is this initial position and velocity. So now I'm going to tell you how to solve that. And this is very straightforward. At least how to find the solution is very straightforward. So let me just start by showing you an example. Yeah, I'm just trying to figure out what example I was going to do. Yeah, okay. So we'll start with an example, and then I'll tell you the general theorem right after that. So I want to find a function y, infinitely differentiable on the reals, such that this differential equation holds. And initially, the position and velocity, which are y and y naught in the spring case, are given by 1 and 1. So this is the initial data. Okay.
Should there be a prime after the 3y?
Yes, thank you. There should be a prime. Good. So, okay, so step 1 is first find the general solution. So in this case, okay, you form this thing, not cube, sorry, r squared. You do, what we already did, r squared. Okay, I don't know what's going on here. And if you solve this, you get r equals, I guess, 4 and minus 1. Yeah. I'll spare you the quadratic formula. We did it last time. And so then, you know that yt, the general solution is a linear combination of exponentials with these constants in the exponent. So c1 e to the 4t plus c2 e to the minus t is the general solution. Any questions about that step? This is not a new thing. Okay. So step 2 is the new thing, which is really not very complicated. Now I need to find a particular y that matches my initial data. So so I need to find C1 and C2, right? So find C1 and C2 real coefficients matching the data. So I need to fit this general solution to the data. So how am I going to do that? Well, I know that y of 0 is 1, right? So let's plug that in, right? So y of 0, that's C1 of e to the 4 times 0 plus C2 times e to the minus 0. Those are just 1. That's C1 plus C2. That has to be equal to 1. Now, what should I do with the other piece of information?
You use it and then you turn it into a system of equations. So
Yeah, so the new thing is you have to differentiate it, right? So here you have to remember that when you do y prime of 0, you do the y prime first, right? It does, because you differentiate the function. So now so what's the derivative of e to the 4t? It's 4e to the 4t, right? So you get 4c1 e to the 4 times 0. And now derivative of e to the minus t is minus 1. So minus c2 e to the minus 0, which is now 4c1 minus c2 equals 1. And now what do you do with this? Well, you row reduce it, right? Okay. I don't remember what the solution to this is, so I hate doing row reduction in public, but okay, I'm gonna do some. I'm just actually in this case I can see you just add the 2 rows and you get something, right? So okay, ignore what I'm doing here. So 5c1 equals 2, c1 equals 2 over 5, c2 equals 3 over 5. So you row reduce, you get c1 equals 2 over 5, c2 equals 3 over 5. And so the solution is y equals this particular linear combination, 2/5 e to the 4t plus 3/5 e to the minus t. So not rocket science. You just write down the equations and solve a linear system. So any questions about this example?
What if it's not 0?
What if the number is not 0?
Yeah.
Then you would plug in that number. So it's a good question. So let me write. So question, what if you have y at some t naught equals some y naught, y prime at t naught equals y1? The answer is same, just plug in t naught. It's not fundamentally different, it's the same thing. So let me write down the sort of summary. So to solve the initial value problem, ay double prime plus by prime plus cy equals 0, and y at, sure, let's just do t naught, y naught. Y prime at t naught equals some initial data. You have 2 steps. Step 1, find the general solution, y of t, which is a linear combination of some 2 basis vectors, right? y1 of t and y2 of t. So we showed how to do that. We know how to always do that. The second step is just fit it to the data. So find C1, C2 by solving really a linear system. So the linear system we're going to solve is y1 of t naught, y1 prime of t naught, y2 of t naught, y2 prime of t naught, c1, c2 equals y naught, y1. This is the general, this is what you'll end up with in general if you do what I did on the previous slide. And you know how to solve that, right? It's just 2 by 2 row reduction. Now there is an interesting subtle point here, right? So before I get to that, any questions about the summary? Sorry, the symbol is and. So there's one thing about this that should kind of, I mean, there's only one thing that could go wrong here, which is why is this linear system, why is this consistent? I claim it's always consistent. Why is it consistent? What have I said?
Oh, sorry. Or I don't know, but like is like the determinant of the A matrix is not zero. So it's
Yeah,
basically
okay,
linearly independent.
that's right. But why are the columns linearly independent?
Didn't we define them to be linearly independent when we found them?
No, because remember, so you know the subtlety is that y1 of t and y2 of t, which are now living in this big vector space, right, are linearly independent, right? But that doesn't mean that when you plug in numbers, you're going to get vectors in R2 that are linearly independent, right? But why are, you know, just to remind you, we already defined a function, right? Why are S of y1, S of y2 in R2 linearly independent? Remember?
S is isomorphic and preserves the linear independence.
Exactly. By the existence and uniqueness theorem, which is that this S here is an isomorphism. So this preserves linear independence. And that implies that this is always invertible, right? So the answer is that S is an isomorphism. Okay, and so the conclusion is that y1 and two vectors in the kernel of T, where T is a differential operator, as you know, as we've been writing, T equals AD by dt squared plus dBd by dt plus CI, are linearly independent if and only if the images that you get by evaluating them at a point are linearly independent. Okay. S is this particular linear transformation on the first page. S is this. Very important. This is sometimes called the evaluation map. You've seen it in homework and exams at this point. It just spits out the value of the function and its derivative. Okay, so this is essentially the fact that this always works is equivalent to the existence and uniqueness theorem. And I should say this is really a special property of differential operators and differential equations. Okay, so let me show you another example. So consider the following functions. So let y1 of t be cosine of t, and let y2 of t just be the function 1. These both live in this vector space, right? Now I can form the matrix y1 prime, y1 of, let's say, 0, y1 prime of 0, y2 of 0, y2 prime of 0. So do you think this matrix is going to be invertible? So by the way, these two functions are linearly independent, right? In this vector space. Clearly, one of them is not a linear multiple of the other one, right? But do you think that these two columns as matrix are going to be linearly independent?
Yeah.
Okay, let's check. So, well, so y1 of 0 is cosine of 0, that's 1. Cosine prime is sine, sine of 0 is 0, right? y2 of 0, that's just a 1 function, that's 1. y1 prime is identically 0, so it's 0. So this is not invertible. So i.e. S of these functions are linearly dependent. What went wrong?
Those functions aren't in the kernel of T.
Exactly.
So
Exactly. The theorem says that this S is an isomorphism from the kernel of T to R2. So this sort of important fact, okay, I'm not sure what just happened. This important fact that linear independence of functions corresponds to linear dependence of vectors in R2 only works when you're in the kernel of a differential operator, right? So the point is that the theorem, so the existence and uniqueness theorem, or okay, the point is S is not an isomorphism. S is only an isomorphism from kernel of T to R2. And these y1 and y2 are not in the kernel of T for any T, which is a second order differential operator. Why not? How do you know that? I mean, I guess this is a proof that they're not, right? If they were, then the theorem would apply, right? But can you tell me another reason why these two functions are not in the kernel, are not both solutions of any second order homogeneous ODE?
Neither of them is of the form like e to the constant t.
Exactly. They just don't, we completely classified what solutions of these equations look like. They have to be one of these things, right? These are the only three possibilities. And what I wrote on that slide is not any of these. So it's not a solution of any second order differential operator. Okay, so the subtlety here is that whenever you say linear independent, ask yourself what vector space, right? So just because the functions are linearly independent doesn't mean, you know, when you evaluate them at some point, they'll be linearly independent. I mean, that's something we knew before midterm 1, right? Applying a linear transformation can destroy linear independence. So, okay. So any more questions about that before I move to the next topic? And I want to add one remark just to be consistent with the textbook and also because it's used in other areas. The determinant of this matrix has a name. It's called the Wronskian. Is called the Wronskian of two functions y1 and y2, and it's denoted w of y1, y2. We won't be using this heavily in the course, but you know, this is something we something that is in the book, for example. And so the existence and uniqueness theorem another rephrasal of it is that y1 and y2, so two solutions of a second order differential equation, are linearly independent if and only if the Wronskian is not 0. For some t. I mean, okay, really it's it ends up being for all t. So let's just write for all t. This is just a side remark. This is not central to understanding of the problem. Okay, I see some discussion in the chat. Very good discussion. Somebody want to ask those questions so everybody can hear?
I guess I can ask them. I was asking, why isn't 1 in the kernel space? And specifically because I thought you could make E of the RT equal to 1 if RT is 0. And
Yeah,
cosine T is not in the solution, 1 is not.
that's a great question. So the question is, well, it looks like 1 is just e to the 0t, right? You're right. So that could be in a kernel, right? Of one of these operators.
Yeah.
But could both of them be in the kernel together?
Oh, okay. I see
Yeah.
why.
Yeah. So not one of the 3 cases. Yeah. So it's very rigid what happens. It's always one of those 3 cases. Okay, so that's the initial value problem. And as I said, inhomogeneous, so I'll just, inhomogeneous, we're actually just simply going to skip inhomogeneous equations. Okay, we're at least going to skip 4.4, 4.5. We'll see in the next lecture, we might say a little about inhomogeneous equations, but for now, we won't worry about them. Okay, the next topic, which I'll begin today and finish next time, is systems of first order linear ordinary differential equations. So just to show you an example of what such a thing, what I mean by this, well, so far we looked at one differential equation. But why should we stop there? Why not look at a bunch of differential equations, right? Example, find some functions x1 of t, x2 of t, from reals to reals, such that, I don't know, x1 prime of t equals 5x2 of t, x2 prime of t equals 3x1 of t minus x2 of t. So these are now unknown functions. And the key difference here, now you have more than one equation. So you have more than one function and more than one equation. Right? Previously you had one function and one equation. Now you have more than one function and more than one equation. First order means no second derivatives. So it's a bit simpler in that sense. Now, why would we study this? So I'll just show you a demo. I'll give you the proof of next time why this allows us to study that. So motivation. There are many motivations. This is like a very important thing that comes up all over the place. Show you a demo. So if you go to this spring simulator.
Professor, we can't really hear you.
You can. Hello?
That's
Yeah.
good.
Yeah,
Okay. So if you go, then there's a next button. And if you click this, you get the next thing, which is a double spring simulator. Okay. So, I mean, yeah, you might do this for fun, but it really is relevant if you want to study things like transmission of waves through air or musical instruments or really all kinds of things. This is a very relevant model, right? If you string a million springs together, you can model very complicated phenomena. And this, this is looks quite a bit more complicated, right? Like this is what the position and momentum look like for this. So this is these are the 2 positions. So how do we understand that, right? And it turns out we're going to be able to do that if we can study systems of linear equations. So let's do that. So the motivation was just this demo, which you can play with, and next lecture we'll see how it connects rigorously. Okay, so again, really part of the goal is the applications, but also just to deepen our understanding of linear algebra, because these are really interesting examples for linear algebra. So let me now turn this into a sort of linear algebra setup. So we're gonna now look at a new vector space, which is going to be vector valued functions. So look at C infinity R to the n to be the vector space of vectors of functions. Okay. So this is a new vector space. And the objects in it, you can think of them in two different ways. Some people prefer one, some people prefer the other. One is that they're just like vectors, like arrays. But now each entry is not a number, it's a function. You can add and scalar multiply those, right? In the obvious way. You can add and scalar multiply, let's say it's a real vector space. You can add and scalar multiply these by real numbers and get more of such functions. Some people prefer to think of it a little differently. You can also think of it as just a space of vector valued functions. So x bar functions from R to Rn, right? So you have x of t equals x1 of t all the way up to xn of t, infinitely differentiable. So this second perspective is you're thinking of it as a vector valued function. So it's an Rn vector valued. If you took Math 53, you're probably very familiar with this because you looked at R2 valued functions and R3 valued functions. But you can look at Rn valued functions. So an example, for example, this here's an example of a vector valued function. This is an element of C infinity R 2 because it's a vector with 2 entries, right? So this is the number of entries, which is the number of functions. So any questions about this vector space? If n is bugging you, just think about 2 for now. Okay, so there are 2 important linear transformations on such a vector space. I mean, there are many, but 2 important classes of linear transformations. There are 2 really important ones. One is differentiation. If you differentiate a vector valued function, well, you just differentiate each entry. And you get a new vector valued function, right? So for example, if you differentiate this, you get, I guess, cosine t minus sine t, which is another vector valued function. Any questions about that? So this is a linear transformation from C infinity R to the n to itself. Now there's a second very different kind of linear transformation, which is just matrix multiplication. Right? So, I mean, okay, it's in the same way, but since we're, I guess, grown-ups now, I might as well write it like this. Matrix is just matrix multiplication. So it's some matrix A. Same thing, take a linear combination, right? So you have x1 of t, v1, plus dot, 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 all the way up to xn of t, vn. So this is a matrix A. So this is matrix multiplication. Let's say this is m by n. Oh, sorry, n by n. It has to be n by n because you want to go from the space to itself. So there are two important linear transformations associated with this. And just to make it concrete, let me do an example. I guess the formatting could have been better, but here's an example of two. Well, I mean, okay, let's just do it here, right? Let's just rewrite. So let's use this new notation to rewrite this equation, right? So what this is saying is that d by dt of this vector, x1t, x2t, equals some matrix, which in this case is going to be 0, 5, 3, minus 2, minus 1, sorry, times this. So it's really not a new thing. The algebra works exactly the same way, except now you have functions instead of numbers. So any questions about what we just did? Okay. So now we're going to try to solve equations like this, right? And, sometimes we'll use the notation, we use an alternate notation for this. We'll also refer to this as x prime of t, where if x is a, vector with these. Sorry, let me write it on the other side. Okay, I guess you understand what I mean. So let me now define the type of equations we're going to solve. So definition, a system of first order ordinary differential equations is in normal form or with constant coefficients is in normal form if it is, written as x prime of t equals ax plus. So I'll put of t to emphasize that these are functions plus f of t, where A is an n by n matrix, let's say real matrix. And x of t is an unknown function, is a variable. Or, I mean, okay, you're looking for x of t in this set. Is a vector valued function, is an unknown vector valued function. Let's write that. And, I mean, again, alternate notation, this is the same thing as d by dt of x of t, right? And again, the terminology is, so if f is 0, then it's called homogeneous. Otherwise inhomogeneous. And we will never do inhomogeneous. So forget about it. F will always be 0. It'll just be x prime equals ax. That's the type of equation we want to solve. So let me put that in a box since it's important. Okay, so any questions about the type of equation? So for example, the thing we wrote on the previous slide, right? That's an example of something in normal form. Because in this case, the matrix A is this, right? This is a 2 by 2 matrix. It's expressing the derivative of a vector valued function in terms of some matrix times a function. And the situation is very parallel to what we did in the second. Sorry, this is f of t. Yeah. Situation is very parallel to what we did in the second order case. So you have two questions. The first question is, what is the general solution? And now again, for fancy notation, i.e. find the kernel of t for t, a linear transformation from now this, slightly fancier vector space to itself by t of x equals x prime. I won't write the little t minus ax. Okay, right? Something being in the kernel is the same as, we're not doing it homogeneous, so just being in the kernel of that is the same as solving the equation, right? The second question is find a particular solution in the kernel of t. So this t again, this underlying differential operator. Find a particular solution with, you know what it does at 0. Let's call this capital X sub 0 in Rn. And this is called the initial value problem for a system of linear ODE. So same two questions, it's very parallel. Just, now we have a bunch of equations and a bunch of functions, and so we have this matrix. Any questions about these definitions?
I'm kind of confusing. Like, how do we know that the function is in Rn? Do we look at the degree?
Yeah, so n is specified as a part of the input, right? So this A is an n by n matrix, right? So we're looking for, of x of t, which is a vector valued function in the C infinity of R to the n. This is not Rn, right? This is a space of functions taking values in Rn.
Okay, I see. Thank you.
If you go back to the slide, right? So it's important to understand this vector space. It's a space of vector valued functions where the vector has n components. So n is, must be specified in order for this to be well defined. Does that answer the question?
Yes.
Okay. And again, we have an existence and uniqueness theorem. Very parallel, which is the linear transformation S going from the kernel of this T to Rn by S of X equals X1 of 0, X2 of 0, Xn of 0 is an isomorphism. So what does that tell us about these two questions? Like the general solution is going to be the kernel of T, right? What's the dimension of the kernel of T? N, because it's an isomorphism, right? So it's very parallel, same conclusions. This implies that this important fact that the dimension of the solution space is always n. And it implies that the initial value problem has a unique solution for every x naught. So it's looking quite similar, and in the next lecture, we'll discuss how to find solutions to these things, which is kind of related in a very beautiful way to eigenvalues and eigenvectors. And that'll actually give an alternate explanation of all of our second order ODE stuff. So that's it for today. Any more questions? So okay, I should say a lot of people are asking about the final. I'll send an email about the final by tomorrow. More details so you can plan accordingly. Yeah.
Do you mind explaining again why we know that the dimension of the kernel space is equal to n?
Sure. Because according to this theorem, there's an isomorphism between the kernel and Rn, right?
Oh, I see. Okay.
And isomorphism preserves dimension.
Right.
So,
Thank you.
Yeah.
Professor, does this only apply if it's if f equals to 0?
This is only if f equals 0.
Okay, if f was not equal to 0, would that mean A has a linearly dependent column?
No. So if f is not equal to 0, that doesn't really have anything to do with A, but it does have something to do with the solution set, right? So the solution set would not be the kernel of T, right? If f was equal to 0, then the solution set is not a subspace, right? Like just like if f is not equal to 0, it's like the solutions of Ax equals B, which is not the same as x equals 0. So when the f is not 0, it's just something completely different. I'll say a little bit about it maybe next lecture.
Okay.
Professor, I have a question about a previous part where you were talking about like y1 equals cosine t and y2 equals 1.
This, yep.
Yes. So you mentioned that y1 and y2 are linearly dependent. I'm wondering like why is that, since like linearly independent means that one is the scalar multiple of the other.
Right. So what I said is that they're linearly independent in this big vector space. Right. So they're indeed independent in this vector space, right? Because if you plot them, one of them looks like this, and the other one looks like this, right?
Mm-hmm.
So they're linearly independent. The claim was not that these functions are linearly dependent. The claim is that once you evaluate them and the derivatives at 0, then you get some vectors in R2. Then those are linearly dependent.
I see. So it's SY1 and SY2.
Yeah, SY1 and SY2 are dependent. And we're
see.
wondering why, why did that happen? Well, the reason is that these functions don't satisfy the theorem, right?
I see.
mean,
Thank
so
you.
there's no contradiction. Yeah.
Mm-hmm.
Professor, just for clarification, you said we're skipping 4.2 and 4.3?
No. We're skipping 4.4 and 4.5.
So do we have to do homework for that too?
No, I'm going to cancel it. I'm going to send an email for it today.
Okay, perfect. Thank you.
Professor, do you mind explaining again why is S an isomorphism?
So, I didn't prove that S is an isomorphism. I just stated this theorem. So the proof is a bit beyond the scope of the course. I mean, I gave a physical explanation for why it should be true, because it's equivalent to saying if you have a spring system and you know the initial position and velocity, then it has if you just let nature take its course, it evolves in a unique way. So that's essentially equivalent to the theorem. So I didn't give a rigorous proof, actually, of the theorem.
Okay, thank you.
Yep.
Professor, I have a question on one of the previous part where we found the solutions for the complex roots.
Mm-hmm.
So when we subtracted the 2 transformation, how did we get 2i?
Well, just look at what happened. Look at the bottom of the slide and what happened in item 1, right? So if you subtract them, the cosines are going to cancel, right?
Mm-hmm.
And the second minus I e to the alpha t sine beta t is going to get its sign flipped.
Oh, I was asking about 2i in the denominator.
Oh, we can just throw that in there, right? No harm.
Okay.
Yeah. We're allowed to do that, yeah.
Okay. Thank you.
Yep.
Wait, are we allowed to do that because we're saying this is a complex transformation?
Yeah. So what the sneaky thing I've done here is I've considered the complex linear transformation T, which is also linear. With respect to complex scalar multiplication. I'm using linearity with respect to complex linear combinations here.
Okay, thank you.
Yep.
Thank you, Professor.
Yep.